So let me record. Has anybody heard anything about today's lesson?
That we're doing math?
Well, of course, that's a given. Oh, it's super exciting. So we're starting a new chapter today, and we're getting into some really great stuff. Not that what we haven't been doing hasn't been great, but we're going to start this chapter by looking back a little bit at some of the parent functions that we have worked with, because as we continue through this semester, we're going to be learning more and more families of functions. And as you know, as we've done in the past, we look at the parent function, we apply transformations, and we get the image function, the result of applying those transformations. And as I mentioned to you before, those transformations can be applied to any and all functions. So we're going to kind of start building formally this library of parent functions. And, What? I thought I heard something. I'm losing my mind now. And we're going to be talking about the next type of function. We're going to be working with polynomial functions. So if you think back to Unit P, we talked about polynomials. We classified polynomials based on the degree, the highest exponent of x, if it was a polynomial of one variable x. We talked about the number of terms, and that is how we classified these polynomials. Oh, I should turn all these off. So let's go ahead and formally talk about this library of functions before we explore polynomial functions. Now, as we move into these new functions, we're going to have new characterizations and ways to describe functions. So in the past, we looked at max, we looked at min, we looked at where it was increasing, decreasing, constant. We're going to, how do I turn this off? How do I limit it? Oh, but it's in Teams, so I have to, oh heavens, they're just going to. Didn't even notice online that I left. A recording has started. Okay. Oh heavens. Sorry. What are they saying? Can y'all see me online? Oh. Oh, well, technically class hasn't started, so we're okay. Well, they're still here, so we're good. Sorry about that, y'all. I had issues. Let's just leave it at that. The notes are in Canvas, so you should see the new notes packet in Canvas. Oh, let me go back here. Or do you mean where are the notes here? Here are the notes here. Let's try this again. Parent functions. All right. So if you recall, what is a parent function? A parent function is the most stripped down basic version of a function in which we apply transformations to get image functions. We've looked at explorations in the past, and we've talked about things that those families of functions have in common. And we're going to start off by looking at the constant function. So the constant function, y equals, or using function notation, f of x equals c, where c is just an element of the reals. This notation you should be comfortable with. So this parent function is just known as the constant function. Now, for every function, if I give you an equation, if you have a feeling about these and there aren't any domain restrictions, any x values that we have to omit, you can always create a table of values, substitute those x values into the equation, and get the corresponding y values. That's going to give you ordered pairs, we plot the little ordered pairs, we connect them, and we see the graph of the function. So if for some reason you don't know what the constant function looks like, well, it says I'm going to pick an x value, and as we see here, c can be any number that is real. So it doesn't matter what you choose, but for all x's that are elements of the real, so that upside down a, remember, is for all x values that are real numbers, the output is just going to be the input. So whatever that c value is, for every x, the output is that c value. So let's look at an example. So if I have an example and I say let c equal 2, then that means f of x equals 2. So for any value of x, that c would equal 2. So what does the graph of the constant function look like? Well, it is a line, but what kind of line? Be more specific. The y equals. So what does that look like? It is a horizontal line at that c value. So this is the graph of the constant function when c equals 2. So that's y equals 2, right? So that's just what the constant function looks like. Now, we talked a lot about some characterizations of these graphs, in particular, the following characterizations. So what would the domain of the constant function be? Not the example, just the constant function in general. What would the domain be in interval form? Yes, or known as the set of real numbers. What is the range of the constant function? The range is just 2. Oh, sorry, C. Yes, we want to do it in general. Right? In this case, 2. Where is this function increasing? Never. Where is this function decreasing? Never. And we're looking to the graph to see where it's rising if we read the graph left to right and where it's falling. But where is this function constant? Okay, and remember, we defined increasing, decreasing, and constant on an open interval. That's what the definition said. So I would represent that as negative infinity to positive infinity. It is always constant. Okay, so there's our first in our library of parent functions. Well, let's look at, another example. The next parent function that we're going to explore is the identity function. What does the identity function look like? F of x, y, right, is f of x equals x. So again, x can be any real number. So if I needed to, I could create a table of values and I could input x. And I know if I substitute in any of these values into the identity function, y equal x, this is going to be a very important function that a function, but a very important line that we're going to be working with a lot for the rest of the semester. If I input these values of x, what do we notice about the output values? It's the same value, right? So if I plot these points, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, etc., whatever the x value is, the y value is the same. And again, this is going to prove to be a very important line in this class and beyond. So let's talk about the domain of the identity function. What is the domain? Yes. What is the range? Same thing. Where is this function increasing? And again, we always define it as an open interval. So notice I'm saying these things so that when we take a quiz or a test and I ask you where this function is increasing, decreasing, or constant, you are representing it as an open interval. These always must be represented using an open interval. That is what the definition says. If you don't do that, you lose points, and it's wrong. Where's the function decreasing? Never. And where's it constant? Never. Okay? 2 down, many more to go. Let's look at the next parent function. And these are ones we've seen or can easily work with. The absolute value function. Now, if you remember, we define the absolute value function as a piecewise function. This is the definition of the absolute value function. So I could have just written the absolute value of x, right? There were 2 cases. The instance when x is greater than or equal to 0. So if the input is greater than or equal to 0, we kept it. If the input was a negative number, less than 0, we took the opposite. So this is the definition we used to define the absolute value function as a piecewise function. Again, if you can't remember what the graph, but all of these you should be able to graph in your sleep, I could substitute in x values. And again, if the input is negative, I take the opposite. If it's 0, I keep it, or if it's positive, I keep it. So again, we should be able to easily graph this without much trouble. Okay, so let's talk about the domain of this absolute value function and every absolute value function. What is the range of the parent absolute value function? Fantastic. And remember, if we transform this, that may change. Increasing, where, ooh, be careful. Where is this function increasing? Open, 0 to infinity, right? So it's increasing here. It's rising left to right here. Okay, what about where the function is decreasing? Open interval, negative infinity to 0. So it's decreasing here. Where is this function constant? Never. Ooh, never. Okay, moving along. Now, this is going to take us to the new types of functions that we're really going to dive deep into. We started talking about these types of functions when we looked at linear functions in the where y is a function of x. The highest exponent of x for a linear function is 1. The highest exponent for a highest exponent of x for a quadratic function in the variable x is 2. If I have a function where the highest exponent of x, where it's a function of x, is 3, it would be cubic, and so on. So where do all of those fall under? They fall under the umbrella of power functions, where I have y, or f of x, equals x to some power. Okay, so if that power, if n equals 1, it's linear. If n equals 2, it's quadratic, and there's the parent quadratic function. And we're also going to look at the parent cubic function. But then we have quartic and quintic, etc. So if I looked at the parent quadratic function, we've done this. We just finished doing this a lot. Again, if you can't remember, you could create a table of values. Oops. And again, you could substitute those values into the parent quadratic function, and you should easily be able to get these values. And you should be able to graph this, oops, that wasn't supposed to be a line, without too much thought. So there is our parent quadratic function. Remind me what the domain of every quadratic function is. Okay, what about the range of this parent? And again, if we shifted it up or down, that might change the range. Where is this function increasing? Beautiful, right? So if I'm looking at my graph, where is it rising left to right? There. Where is this function decreasing? Very good. So it's falling here, and we will have to do that. We'll have to identify those intervals. And where is it constant? Never. Okay, so now let's look at the parent cubic function, cubic power function. So that means I have a function of x, where x is raised to the third power. That's my highest power of x. This is the parent, but there could be more things applied to this parent, transformations. Again, if I don't have any issues with the domain values I can just choose any x values I want, substitute in, and see what our outputs are going to be. If I substitute in -2 for x, what is y? And what about -1? 0, 1, 2. Let's plot those points. And again, we can go off the little Cartesian plane that's represented because it goes on forever and ever. There is the graph of your parent cubic power function. That's the parent. Boy, will you work with this a lot. And again, I could do all sorts of things. I could shift it to the left or to the right. I could reflect it across the x. I could reflect it across the y. I could do lots of things. I could stretch it. I could compress it vertically and horizontally. But let's talk about the domain of this parent cubic power function. What is it? Okay, range. Where is this function increasing? You are absolutely correct. Everywhere, right? If I read that graph left to right, it's always increasing in y values. So where is it decreasing? Never. And constant? Never. Okay, so we've just added the cubic power function, and we're going to really explore those power functions to get the polynomial functions that we will be working with in this unit. Okay, so the next parent function that we're going to add to our little formal library of functions is known as the square root function. So if I look at the square root function, y, or f of x equals the square root of x. And again, I could transform it, but do I have any restrictions on the domain values of the parent square root function? Are there any x values that have to be omitted that would make this function undefined on the real Cartesian plane?
So negative,
radicand? Yes, the radicand has to be greater than or equal to 0, right? And so that is how you will, in the future, determine what the domain is. So that means I can choose anything that is 0 or greater than 0. And since I'm working with the square root function, I'm going to be very clever about the x values that I choose. And I'm going to choose perfect squares, which will make it easy for me to take the square root of to get my ordered pairs to plot. So if I substitute in 0 for x, I get 0. 1 for x, I get 1. If I substitute in 4 for x, what do I get? 2. And 9. And let's plot them. Again, as we build these, there's going to become a time where you really have to be able to just do quick sketches of these without having to think too much about them. There's my parent square root function. It's beautiful. Let's talk about the domain. What's the domain of the parent square root function? Beautiful. Range? Beautiful. Where is this function increasing? What? It's open, right? Because remember, the increasing, decreasing, and constant all we define on an open interval. So see right there where you could lose some credit, right? If we don't remember the definition. Where's this function decreasing? And where is it constant? Beautiful. Well, if we're going to talk about the square root function, we should talk about the parent cube root function, where our root index is now 3 instead of 2. So if I have my parent cube root function, f of x equals the cube root of x, do I have the same domain restrictions as I did for the square root function where the root index was 2, an even number?
Yes.
I do?
Oh, wait, no.
No, I can have negative x values. Lydia, that was kind of a trick question. And again, I'm being very clever about the values I'm choosing to substitute in for x. I'm choosing perfect cubes, or I would, to make my life easier. But it doesn't matter which values you choose. If I substitute in -8 for x, what is the y value? What number times itself 3 times repeated? -2. What about -1? 0 is 0, 1, and for 8, 2. So I'm graphing my parent cube root function, plotting these points. And again, these are the kind of things that we should be able to kind of do in our sleep. And I'm kind of estimating the 8 out there just to give you a quick sketch of this. That is your parent cube root function.
So it's just like the x cubed, but on the x-axis.
Very interesting that you say that. Well, I wonder what the relationship between those two are. Since you said it, how would I write this with a rational exponent? X to what power? How would I solve for x? I'd cube both sides, right? So what would that give me? X equals y cubed. Well, I can't. So if I were to, well, if I were to rotate it, right? The y is now cubed instead of the x cubed. So Cooper, you just brought up a beautiful relationship between those two. So this was an aside. You don't really need to know that right now, but since you mentioned it, I have to talk about it. Domain of the parent cube root function is what? Range. Where is it increasing? And we write it as an open interval. Decreasing and constant. Okay, now this next one, we're building this library. This next family of functions, we are going to spend so much time on, and it's got such amazing things that you will see. So you'll just have to, I don't know how you'll be able to sleep after this. You're just going to be waiting for it. Reciprocal, or better known as rational function. Y equals 1 over x. So what this will lend itself to in the future are functions where you have polynomials in the numerator, polynomials in the denominator. You're going to get to factor the numerator, factor the denominator, look for common factors. That's going to represent itself in beautiful things on the graph. These graphs get just exciting. Wait for it. Rational functions. But the parent rational function, parent reciprocal function, stripped down version. Now I'm going to have to create a table of values. Is there anything that I need to be abundantly aware of? Are there any x values, domain values that perhaps are undefined that I need to omit from this table based on this function? They can't be negative? Yeah, they can be. They're defined. What is the one value that would make this function undefined? X equals 0, right? If x is, oh, heavens, if x is 0, and I substitute in here, I'm dividing by 0, and that's undefined, right? So that is not part of the graph. I'm sorry? It is an asymptote. We're going to get to that. You are correct. So I'm just going to put a little dashed line saying it's not defined there. And again, we will dive deeper into this family of functions, just not right now, but we're building our library of parents. So let's go ahead and substitute in some other values. So maybe negative, heaven help me, -2, -1, 1/2, -1/2, 1/2, 1, 2. Let's substitute those values in and see what the outputs are. -2, if I substitute in that -2 for x in the parent function, what is the output? And if I substitute in -1, -1. What if I substitute in -1/2 for x? I'm dividing by a fraction, so really multiplying by the reciprocal. What is the output? Is it 2? -2, right? Does everybody see that?
No, not quite.
Okay, so if I have 1 over, and I say I'm substituting in -1/2, this is the same thing as 1 times -2 over 1, the reciprocal, right?
Yes, that makes
Because this is 1 divided by -1/2.
sense. Okay.
So this is just 1 times -2, which is -2. Thank you for asking. Do we see it, everybody? Okay. So 0 we said was undefined. 1/2, if I substitute 1/2 in for x, what is y? And 1 and 2. Okay, so now let's start plotting and see if we can see a trend. We said it was undefined. So if I look at numbers to the right of 0, I'll go ahead and start over there. When x is 1/2, I'm at 2. When x is at 1, I'm y equal 1. When x equals 2, it's 1/2. So I notice that it's getting ever so close to that x-axis, but it is never going to be y equals 0. Never going to happen. So it's going to get closer and closer and closer to the x-axis, but it's never going to cross it. Look at the function and kind of make sense of that. To the left of the y-axis, okay, if I'm at -1/2, my y value is -2. -1, I'm at -1, and so on. Something similar is going to happen here. So I'm going to get closer and closer to each of these axes, but I will never cross it. So that means that there's, something else going on here. And again, we will explore that when we get to rational functions. I'm telling you right now, though, algebraically, looking at that function, do you see how as x gets bigger in the negative direction, I get tinier and tinier fractions? As x gets larger, getting closer to 0, I will get closer to 0, but I will never become 0. Then immediately to the right of the y-axis, when x is teeny, 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 tiny, I'm dividing by something teeny, 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 tiny, so I'm huge. And then as x gets bigger, my fraction gets smaller in value. So I get closer and closer and closer to 0, but I will never be 0. These functions are I love them. All right, let's talk about the domain. For what x values is this function defined? Domain. But it doesn't include 0, right? We said it was undefined at 0. So -∞ to 0, yes, Austin, union 0 to infinity, right? So it goes all the way up to 0, but it doesn't include 0 on either side of the y-axis. So do we see the two little different intervals of x values, right? Here and here. Okay, let's talk about the range of this parent rational function. What is it?
Is it the same thing?
It is the same thing. Absolutely. You are correctly. It's the same exact thing, right? So if I'm looking here and I'm looking at my y values, oops. Define, 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 not at 0. Define, define, define. Now, where is this function increasing, if ever? It is never increasing. The y values, as we read the graph left to right, are never getting larger. Larger in the negative direction to the left of the y-axis, but not larger in value. Where is this function decreasing? Everywhere that's not 0. So again, we define this on an open interval, so we have to write the same interval that we have for domain and range. Where is this function constant? Never. So be on the lookout when we get to the unit with rational functions. Super exciting. Now the next one, how many people in here have had computer science? Nobody. Nobody? Okay. Well, then you may or may not have seen this greatest integer value function. y or f of x equals the special notation. Double struck bracket around x. So what in the world does that notation mean? What is the greatest integer function? Well, there are no restrictions on x. I can put anything in there as the input. So for all x in the set of real numbers, what this function is returning, what the output of this function is, and let me go ahead and write that out. The greatest integer function takes any x value as its input and returns output the largest integer less than or equal to x. The greatest integer function takes in any x value as an input, and the output is the largest integer less than or equal to that input. Oh my gosh, what does that mean? Well, in other words, what you're really doing is you're rounding down. So the greatest integer function rounds down a real number to the nearest integer. Let's do a few. So let's look at some examples. I like to think of it on the number line. So for each of the numbers, I'm going to look at it on the number line because I think that will help you understand what the greatest integer function does. It's saying take 5.9 and round it down to the nearest integer. So if I'm at 5.9, I'm between 5 and 6, right? I'm kind of like right here. If I want to round that down to the nearest integer, what is the nearest integer less than or equal to 5.9? 5, right? So it rounds it down to 5. Just take that number inside that notation and round it down to the nearest integer. Okay, what if I give you 2.3? So I go to 2.3, I'm here, I'm rounding down. What's the nearest integer below that? Okay, good. What if I give you 7? It just would be 7, right? Okay, here we go. What if I give you negative 3.6? Okay, so let's go ahead and look at negative 3.6. So I'm between negative 3 and negative 4, right? I'm rounding down, so I'm always looking to the left because that's less than, right, on the number line. So what would that be? Negative 4, right? So do you see what that greatest integer function does? Okay. Now, what on earth does the graph of the greatest integer function look like? Well, let's build it. Let's think about it and let's build it. If x is 0, if my input is 0, my output is 0. It's an integer, right? As I increase all these little fractions, I'm still going to be rounding down to y equals 0, right? But as soon as I get to 1, my output is 1. Does that make sense? Okay, so when I'm x, my input x is 1 and 1.1, 1.2, 1.3, 1.4. I'm still rounding down to y equal 1, but as soon as I get to 2, I'm at y equal 2. 2.1, 2.2, 2.3, 2.4. I'm still rounding down to y equal 2, but as soon as I get to 3, I'm here. Do you understand the graph of the greatest integer function? Does anybody not understand the graph, how we arrive at this graph? We could represent this as a piecewise function, couldn't we? Those are little pieces. I'm lifting my pencil and putting it back down to get to the next part of the graph. So this is a piecewise function. It's also known as a step function. Very famous. And now the steps can get longer. There's all sorts of crazy things that happen with these beautiful step functions. You'll study those in pre-cal. Now let's be ever so careful and describe the characterizations of this function, this graph. The domain of this greatest integer function is what? Domain. Negative infinity to positive infinity. What is the range? And range, again, are your outputs, your y values. What is the range? And be careful. Think about it. What is the range? That's a y value, y value, y value, y value, y value, right? These are all y values that the function takes on. What would it be? How would I represent the range of this greatest integer function? How would you describe those values? They are, well, they're discrete values. Yes, they are. Not real. Is negative 1/2 in the range? Is 4.5 in the range? No. What type of numbers are in the range of the greatest integer value function? Integers. So what is the range? Integers. Greatest integer value function. It makes sense, right? It returns integers. So if it's returning integers, its output are integers and only integers. So my range is only the set of integer values. Yes, Kia.
Is that a C?
It's a Z, right? Double struct Z there, Cooper. Machine. All right, here we go. Where is this function increasing? Never. Very good. Where is this function decreasing? Never. Oh my goodness, but where is this function constant? Really?
Would it be like
All these little pieces, right? That oops. This little interval, it's increasing in that interval, in this interval, in that interval, in that interval, in that interval, and all these little intervals, right? Because we have to define them on open intervals. So how would I represent that? Well, I know it's increasing. I don't know, I can start here, -3 to -2, union, -2 to -1, union, -1 to 0. I could go on forever and ever and ever. No, you have to still define it. This is how I would define it. The fact that I have created this pattern, I have 3 of these, I can just write union ... on either side.
Oh, so you don't have to write them all?
No, but you have to write enough for me to see that you have to write like 3
Okay.
or so, right? So we're building our library of parent functions. These parent functions, if someone walks up to you on the street and says, what's the greatest integer value function? Or where is the greatest integer value function constant? You should be able to explain it and draw a picture. Same thing with the parent cubic function, parent square root function, etc. These should be common knowledge to you. So what I'm going to ask you to do for class next time, because we're going to continue on with the notes. This is an exploration that I would like you to do, yet another beautiful exploration. I would like you to explore power functions, okay? So that's y = x to the first. Then we're going to look at y = x squared, x cubed. So y = x to the n. The power function is y = x to the n, and we're varying the values of n. We're increasing the values of n. You are going to get this table of values for each of these, and then you are graphing them if you'd like on Desmos is fine. But I want you to notice what is shared among these tables of values. So you're investigating the tables of values, maybe looking at some stationary points, points that don't really change as we increase the powers of x. And then I'd like you to do a quick little sketch for each of these. Just a quick, as you do it on Desmos, do a quick little sketch for each of these. See what they look like, because I want you to recognize something, okay? Once you've done that, and you can put them all on the same Cartesian plane in Desmos, answer these questions. Okay, this is a little exploration. I'd like us to discuss this exploration at the beginning of class next week. Okay, so this is due. The power exploration is due for class next class period. Okay, but let's go ahead and let's talk about very special functions. So I would like to talk about some very special functions. So as we talk about functions, we talked about different ways we can classify these functions. Well, there's more classifications that we can use. Now, with these power functions, we know that we're looking at x to some power. Maybe x to the first, to the second, to the third, x to even numbered powers, x to odd numbered powers. And you're going to notice something in that power exploration. But I'm going to give you another way to classify functions so that as you are doing those, you can maybe think about how you see them graphically, these special functions, and how you can represent them and verify that algebraically. So what we're going to talk about next are very special functions, even functions, odd functions, or neither. So you don't have to be even or odd, you could be neither. But if I were to give you a function, a graph, or an equation, graphically you should be able to recognize if it's even. Algebraically, you should be able to verify or determine if it's even. If it's not even, you're going to check to see if it's odd. Again, we can look at it graphically and maybe get an idea, but algebraically, there is a way to verify or determine if the equation represents an odd function. If it's neither even nor odd, and you have justified that, you would say that it's neither. So you don't have to be even or odd. You can be neither. Only special functions are even or odd. Okay? So let's talk about, first of all, what it means to be even. If you are an even function, you are symmetric about the x. That means if I'm folding my graph on that y-axis, symmetric about the y-axis, if I fold my graph along the y-axis, I'm going to get a mirror image. So algebraically, what does that mean to be symmetric about the y-axis? Well, that means algebraically, I can prove this for all values of x in the domain, all my domain values. So what does this mean? That's saying for any x, f evaluated at the x, the y value is the same for the positive and the negative value of x. So if I'm here at positive x, notice my output is y. This is a value. If I go same direction but on the other side of the y-axis, negative x, the corresponding y value is the same y value. So f evaluated at x equals f evaluated at that negative of x, the opposite of x. Does everybody understand what this means? Okay, so if I were to give you a function, you could look at the equation, you could take out all the x's and replace them with negative x's, and if you get the same equation when simplified, it's even. If not, we have to check to see if it's odd or if it's neither. Graphically, if I look at this, if I see symmetry about the y-axis, I know it's even. Well, I didn't want to verify it, but I could tell this is even. Now, just because you have an even powered exponent, an even power of x, if I'm talking about the parents, they're even. But if there is anything else, just because you see x squared, it doesn't necessarily make it even function. Like x squared plus 1 minus 2x, et cetera, et cetera. If I've transformed that in any way away from the parent, if I've applied any transformations, just because the highest exponent of x is even does not make it an even function. You'd have to show this algebraically. So there's many even functions out there in the real world. In pre-cal and beyond, you're going to see something known as the cosine function. This is a nice, beautiful little periodic function. And if I were to fold this graph along the y-axis, I would get mirror images. So I would get f evaluated at x, and f evaluated at negative x would give me the same y value. F evaluated at x, f evaluated at negative x would give me the same y value. So it's symmetric about the y-axis. So if I were to give you this next function and I ask you, determine if it's even, odd, or neither, well, right now we're just talking about even. So I'd have to see, is it even? To determine if this is even on the quiz or the test, if you are being asked to verify if something is even, you need to show f of x equals f evaluated at negative x. Okay, so what is f of x? F of x is x plus 1 quantity squared. If I FOILed that and simplified, what would I get? Because this is x plus 1 times x plus 1, so I'd FOIL, and I'd get what? Okay, so that is f of x. Now, everywhere I see an x in the original function, I'm going to replace it with negative x. I'm going to simplify that and see if it equals this. If it equals that, it's equal. It's even. If it doesn't, it's not even. That's all I can say. It's not even. So I'm going to come back into this, and I'm going to replace my x with a negative x. You see how I've replaced my x in my original function with negative x. So then that means I'm taking this and I'm saying negative x plus 1 times negative x plus 1, right? If I FOILed that, what would I get? Are these equal? No, so it is not even, right? Because we have shown that this is not true. Now, is there a shorter way I could have done it instead of actually going back into the original function? I could have taken this version and I could have replaced each of these x's with a negative x. And I'd still get x squared minus 2x plus 1, right? So it doesn't matter which way I do it. The key is it's not even. But this is what you would have to show to state that it is even algebraically. You need to show this. If this is false, it's not even. So this was false. So all I can say is it's not even. Now, if I were to give you a graph, you should be able to see it. Now, looking at the graph of this, the parent is this, right? Y equals x squared. If I were to give you this equation, the stripped down underlying parent function is y equal x squared. But looking at this, what has happened, it's been shifted to the left one, right? I can recognize that transformation. Is that symmetric about the y? No. So, I mean, if you can go about this so many different ways. I can look at the function. I can say, ooh, it's a quadratic function. It's a transformation of a quadratic. I could graph the parent quadratic, which is y equals x squared. Yeah, I know that's an even function. I can algebraically prove it. I can look at the graph. But knowing in my heart of hearts what transformation has occurred here, it's been shifted left to the 1. I again can look at it immediately. I don't have to do any algebra unless I wanted to verify it, that's not even. Do we understand what it means for a function to be even, algebraically and graphically? Okay, let's look at more examples. So instead of even functions, what does it mean for a function to be odd? If being even means it's symmetric about the y-axis, what does it mean for it to be odd? For it to be an odd function, I have to show something else. And you could probably try to guess what it means to be an odd function, but I'm just going to tell you. To be an odd function, I have to show this. It means we have origin symmetry. What is origin symmetry? Symmetry about the y-axis and the x-axis. So that's what it means to be symmetric about the origin. That means it's a reflection across the y and the x. So what does that mean? If I take x and I look at f of x, if it were symmetric about the y, it would be here, right? But it's not symmetric about just the y. It's not even. It's also symmetric about the x. So this is actually rotational symmetry, symmetry about the origin, which means reflection about the y, reflection about the x. So I would have to show this. Now, a lot of people like to take a shortcut, and to find that it was even, recall, if it's even, means f of x equals f of negative x. Well, if you go through the process of saying that that is not satisfied, what I can do, well, if I divide this by -1 and divide this by -1, don't I get f of x equals negative f of negative x? All I did is, I know I have to show this to prove that it's odd. If I divide each of these by -1, don't I get this? An equivalent equation? Yes or no?
Yes.
Okay, all I did was I started here, I divided each of them by -1, and I got this. The reason some people like to use that version to demonstrate something is odd is because I've already established this. So if I just negate this, I can prove that it's odd. I'm just putting a negative in front of what I've already done to find if it's even. Does that make sense? That's kind of a shortcut. That's why I like to use that version. So an odd function means it's symmetric about the y and the x. It's symmetric about the origin, around the origin symmetry. So if I look at this example, this is saying that another periodic function, a very famous one, is that, look here, when I'm at x, there's my y. It's not here, it's here. So do you see how it's symmetric about the origin? That's what it means to be an odd function. Now, parents power functions that have an odd exponent are odd functions. But if I've done any transformation to it, it may or may not keep it odd. So we would have to verify it algebraically. So let's say I give you this function. If I wanted to show that it was even, I would have to show f of x equals f of negative x. If I wanted to show that it was odd, I'd have to show f of x equals negative f of negative x. Or it could be neither, if neither of those two are satisfied. Because remember, you don't have to be even or odd. So let's take this function. My original function is x cubed plus 1. To try to demonstrate that it's even, I would take the function, and everywhere I see an x, I would substitute it with negative x. You see how I just took out the x and I replaced it with negative x. What is negative x cubed? Negative x times negative x times negative x. Does that equal f of x? False. So it's not even. Okay, but I have this. So I can just take this and substitute in for this, right? And just negate that. You see how nice that is? So f of x again, we said was x cubed plus 1. The question is, does this equal the opposite of this? You see how I'm just taking what I used to find if it's even, to determine if it's odd? Okay, so let's see. Let's simplify that. I'm distributing the negative, so what do I get for my first term?
X cubed
And my second term?
minus 1.
Are these equal?
No.
So it's not odd. So it's neither, right? So that's how you can verify if a function is even, odd, or neither. Oops, yeah. Now, there's some very special properties that will help you. So you can try this one as an example, determine if it's even, odd, or neither. Do we want to do that together, or do you want to try that now? Go ahead, try it. Tell me if it's even, odd, or neither. That's good practice. So if it's even, I need to show f of x equals f of negative x. If it's not even, I try odd, and I would need to show f of x equals negative f of negative x. If neither of those are true, it's neither. So try it. Well, I've only shown so far that it's not even. But yes, you are correct. Do we all see how it's neither? So you have to go through that process. Check if it's even. If it's not even, check if it's odd. If it's not odd, it's neither. Now, there's some special properties where you don't actually have to do any work when we're doing operations with functions. If you are dealing with adding two functions, if the two functions are even, you get an even. If the two functions are odd, you get an odd. If you add an even and odd, well, it's neither even nor odd unless one of the functions is 0. With respect to multiplying, if you multiply two even functions, the product is even. If you multiply two odd functions, the product is even. If you take the product of an even odd function, the product is odd. So some people like to think of this in terms of the similar outputs. If you're doing multiplying two positive, being even, two negative, right? Two odd. So some people like to equate that. Now, what I'd like you to do now in class is I would like, and here's some more practice for you at home. So go ahead and try those. But I'd like you to do the worksheet. Even, odd, or neither. We're doing this now. Now the graphs you can easily look at, easily determine whether they're even or odd based on the symmetry, right? If a graph is not given and you really don't know what's going on, you're going to have to be able to algebraically verify each of these. Go ahead and do these quickly. They shouldn't take that long. Again, with all of them, you should be able to verify them algebraically, and I'd like to go over them in class before we leave today. So let's go ahead and look at these now. Even, odd, or neither. For all of these, you should be able to algebraically determine them and verify. Even, odd, or neither. Take about 5-10 minutes to do all of these on these 2 pages. for each of them, you should be able to verify algebraically, because on the test, you have to verify algebraically. So again, for each of these, if you're given a graph, you could kind of tell, but make sure you can algebraically verify each of them. So for every problem, even though you can tell, make sure if it's even, you can show this, implying symmetry about the y-axis. If it's odd, you need to be able to show this, demonstrating origin about the symmetry about the origin.
So if we can tell the graph but it doesn't specify to verify, you don't have to.
On the test, if I don't ask you to verify, you can just explain it is symmetric about the y-axis, therefore it's even. You better believe on the test, you're verifying everything. So I may give you something, you may have to graph it first to help you see, but then you will have to verify algebraically for everyone on the test. If you get stuck, you can discuss it with a math friend. But I'd like to go over these before we leave today. Front and back. Make sure you can verify algebraically. Bless you.
Thank you. After you've done these 2 pages, if you want to go ahead and start on the Desmos or fill out the table of values, at least on the power exploration, you can, because I don't really want to rush anybody, but I do want to go over these before we leave. Yes, we're doing the back, front and back. So we're doing this and we're doing that. Again, once you finish this, if you want to go ahead and fill out the table of values for the power exploration, to get a head start, you can. There is also my math lab on this, even, odd, and neither. Cece, did you ever find the notes on Canvas?
No.
No.
Yeah.
Did you go to Unit 7 module? And
Okay.
then there's your blank notes packet in Unit 7 module.
I can't find the Unit 7 module.
Of course. Okay, tell me, do you see it now?
Yeah, now I can see it.
Okay.
Thank you.
Sorry. Are we ready to go over these? Or are we still working? Okay. Lucy, did we get them? Kind of, maybe. Okay, let's go ahead and go over them, and then the ones you haven't had a chance to do, at least make sure you can get the result that we got. Is the first one even, odd, or neither? I can't hear you. Neither. Second one? Third one? And again, we can see the symmetry, but we should make sure that we can actually prove it or verify it algebraically. The fourth one, even, odd, or neither. Fifth one, sixth one, seventh one, eighth, ninth one, 10th one, 11th one, and the 12th one, neither. So make sure that you can get these results and that you can algebraically verify them and describe the symmetry. That is important. So if I give you an equation of a function, can you determine if it's even, odd, or neither? On the test, you will say, to show it is even, I need to show. You will state this statement. You will do the calculations, and then based on the result of the calculations, you should be able to draw a conclusion and geometrically describe what's happening, or explain geometrically what's happening. So I'm telling you what I'm looking for on a quiz or a test. You have to state what you're showing, the algebraic identity that we're showing, show the math, draw the conclusion, and explain what the conclusion tells you about the graph. All right, so you have Desmos power exploration to finish and my math lab. For class next week, you need to have the Desmos done. We will start with that and move on with the notes. However, your homework, you have a few extra little days to do the homework. Since I think I made it due Friday, so you still have time to work on that. Okay? Excellent. You guys online, any questions? Are we good?
No, ma'am.
All right. I will see you next time. Y'all have a good rest of your day.